सुस्वागतम, नमस्कार, केम छो, आदावर्स, a very good morning, good afternoon, good evening, depending upon which part of the world you are. आप सभी को राष्ट्रीय युवा दिवस यानी कि नेशनल यूथ डे की बहुत बहुत शुभकामनाएं, बहुत बहुत बधाई। आप सभी का पीआरएल के अमृत व्याख्यान में स्वागत है, अभिनंदन है। A very warm welcome from me, Anil Bharadwaj, to the 24th Vyakhyan of the 75 episode series of Vyakhan, which is being organized by PRL as a part of 75 years of legacy and history in fundamental physics and space sciences. Established in the year 1947 by the father of Indian space program, Dr. Vikram Sarabhai, the PRL's Platinum Jubilee coincides with India's 75 years of independence. So it's a joint celebration of development of science and technology in India by PRL under the banner of PRL का अमृत व्याख्यान. Today's व्याख्यान is a very special one because it is being held as a part of India's first space weather conference. Today is the second day of this conference, and this व्याख्यान and the speaker is the most apt one because he is going to speak on the topic societal and economic impacts of space weather. So today we have a very distinguished speaker, Professor Daniel Baker, Director of Laboratory for Atmospheric and Space Physics at University of Colorado in Boulder. And let me tell you two things about him. My colleague, Professor Pallam Raju, will be anyway introducing him. Firstly, that he has been in PRL as Professor Vikram Sarabhai Professor in the year 2019. And secondly, that he did his PhD under Professor James Van Allen. And we all know very well Professor James Van Allen. So with this, let me welcome Professor Daniel Baker for PRL Kamrit Vyakhyan, as well as to Indian first space weather conference. Thank you, and over to you, Pallam.
Yes, thank you. It is indeed a great pleasure and an honor for me to introduce today's speaker, Professor Daniel Baker. Professor Baker is the director of the Laboratory for Atmospheric and Space Physics at University of Colorado Boulder. He is a distinguished professor of planetary and space physics at CU, and is a professor of astrophysical and planetary sciences, professor of physics, and professor of aerospace engineering sciences. Dr. Baker received his PhD working under Professor James A. Van Allen, and subsequently worked with Professor Edward C. Stone at the Caltech. And he was a group leader for space plasma physics at Los Alamos National Laboratory from 1980 to 1987, and was division chief at NASA's Goddard Space Flight Center from 87 to 94. Dr. Baker presently holds the Moog Broad Roche Endowed Chair at Space Sciences at CU. He has edited 9 books and published over 800 refereed papers. He is a lead investigator on numerous NASA space missions such as RBSP, MMS, and IMAP. He is an elected member of the US National Academics, NASEM, and Dr. Baker was the 2010 winner of the AIAA James Van Allen Space Environment Medal. In 2015, we had the pleasure of hosting Dr. Baker as the Vikram A. Sarabhai Professor at PRL. Dr. Baker has received numerous awards like Shenko Medal of the International Association of Geomagnetism and Aeronomy, IAGA, and his interdisciplinary work in space and earth sciences. He also received Colorado Governor's Award for high impact research related to his space weather research in 2016. Dr. Baker was awarded the American Geophysical Union's highest honor, the William Bowie Medal in 2018, and the Hans Alfvén Medal of the European Geophysical Union in 2019. with this brief introduction, I would like to invite Dr. Daniel Baker to deliver his talk, Societal and Economic Impacts of Space Weather. Professor Baker, please, over to you.
Thank you so much, and thank you all for being here for this presentation. I'm delighted to be here. I wish I were there in person. I'd love to be back visiting PRL. I've had wonderful visits there, and I have enjoyed thoroughly the interactions with scientists at PRL. I'm pleased to be able to be a part of this inaugural set of meetings about space weather for all of you, and I'm looking forward to questions and interactions about space weather. I thought I might start by saying a little bit about my institute, just to put in context what we do and how we do things here at see if I can get the slides to advance. There we go. So the Laboratory for Atmospheric and Space Physics, or LASP, is a research institute of the University of Colorado. We presently have about 700 employees. We have at any one time about 150 or 160 students that are working in the institute. And we have about 250 active affiliates, and so we have quite a range of areas that we work in. The science really leads our activity, and this is science in planetary research and atmospheric research, solar, and now more stellar. We're working a lot on extra solar system planets, exoplanets, and space physics. An important component of that is space weather, which I'll talk about this evening. In order to accomplish these things, we have a large and very capable engineering staff. We have outstanding, I think, test and calibration facilities, and then we are operating numerous spacecraft for NASA and NOAA. We just have been initiating a new mission, the XP mission, that is imaging X-ray polarimetry experiments. So we're actually doing operations for not only planetary missions, the Emirates Mars mission in orbit around Mars, but also astrophysical missions, and then doing science operations for the magnetospheric multiscale. So it's quite a diversity of different things we're doing. The ecosystem that we have for space-related research and education at the University of Colorado, or in the Boulder Front Range area of Colorado, is really quite exciting, and offers a lot of opportunities. On this slide, you see a number of the major departments, academic departments, that have a strong involvement in space research. But you also see that there are national centers and national administrative entities. There are labs from the National Oceanic and Atmospheric Administration in Boulder. There are labs for the National Institute of Standards and Technology, and joint institutes there. LASP is the highest funded of the research institutes. We're not affiliated directly with NASA, but we get a great deal of our support from NASA. We also are delighted that the National Solar Observatory, sponsored by the National Science Foundation, has moved its headquarters to our building on the Boulder campus. And we work closely with the National Center for Atmospheric Research. And so this ecosystem offers immense opportunities for collaborative research across many different kinds of science and areas. But tonight, this morning for you, I would like to talk about the Sun-Earth connection. I'd like to talk about the topic of space weather. And I like to show this diagram. There are sort of two branches to this. One is the research branch, the sort of upper branch that you see here. This is a picture of the sun in soft X-rays. I should hasten to point out, I think all of you realize that the Earth is not this large relative to the sun. It's not that close to the sun, fortunately. Other than that, it's a perfect picture. But we study the interaction of the sun and its effluence with the magnetospheres of the Earth and the other planets. We do comparative studies of atmospheres of the planets, and we extend the knowledge we gain in our own cosmic backyard to the plasma universe. And so that's the basic research branch. But there's another very important component of this, and this is the branch here that is the more applied branch, understanding the effect of the space environment on humans in space, satellite operations, power and communication, climate change even. And so understanding the practical effects of the space environment on human technology is a very important component. And this is what is referred to as space weather. So space weather is sort of like terrestrial weather, and people talk about it a lot. And there have been a lot of remarks about weather that by pundits. For example, Oscar Wilde said conversation about the weather is the last refuge of the unimaginative. I suppose that might be sort of true about space weather as well. On the other hand, American humorist Ken Hubbard said, "Don't knock the weather. 9/10 of the people couldn't start a conversation if it didn't change once in a while." And again, that's perhaps relevant remark about space weather as well. But this topic of space weather has been addressed by a lot of policymakers, and the U.S. National Space Weather Strategy that was published a few years ago has given a pretty good description of what space weather really is, the conditions in space that affect human technology. It can potentially disrupt power systems, satellites, aircraft, spacecraft operation, communication, nav systems, and a whole host of other technologies. And so my goal tonight, in I hope in fairly brief fashion, will be to discuss a lot of these aspects. And you probably are aware of many of these yourself, but trying to give this in a fairly coherent way is the objective of this lecture this evening. One could argue that our sun, the sun, is the most important star in the universe from our point of view, at least. And of course, space weather really starts there. Energy that's provided by the fusion reactions or so for energy that's initiated in the center to make it out through the radiative zone. This then gets out to the outer part of the sun, which is more convective in character. The sun, the gases on the sun rotate more rapidly at the equator than they do at the pole, and this leads to large overturning and the dynamo action. This really generates all kinds of motions up and down, welling of plasmas on all spatial scales that we can see. It can also lead to hot spots, sunspots with intense magnetic fields that can emanate from the surface during certain parts of the 11-year activity cycle of the sun. These sunspots can be associated with strong magnetic fields. There can be large outwellings of plasma from the surface of the sun, prominences that dwarf the Earth in their size. And the bright patches that you see here are also sources of strong magnetic field. The overall magnetic field of the sun is crucial, of course, for effects of space weather. And then large blasts of material called coronal mass ejections that we'll talk more about, that if the Earth is in the sites of such blasts of material, this can cause severe space weather in the Earth vicinity. And the shifting and interaction of emanating magnetic fields on the sun can give rise to powerful solar flares that can produce intense radiation that travels out into space and can affect satellite systems and humans in space and all things like that. The sun undergoes an 11-year activity cycle. Why it's 11 years for our sun, why it's not 8 years, or why it's not 20 years is not altogether understood. But this is a sequence about a year apart of images taken in soft X-rays by the joint Japanese-US spacecraft Yohkoh. You can see at the height of the sunspot activity, the sun is very bright and active in soft X-rays. A few years later, that's very quiescent, and then it rises back to high activity. And so this kind of activity cycle is a dominant feature of the occurrence of different kinds of space weather. Now, we've been in a golden age, I would say, for understanding, for seeing the sun. We've had spacecraft that have been taking truly remarkable images in a variety of wavelengths and in a variety of ways to see the sun, to see the active regions, to see flares, to see coronal mass ejections. And it is really, over the last couple of decades, we've had a tremendous opportunity to study many of the aspects of the sun that are space weather drivers in exquisite detail. One of the most interesting things, as I say, is really when there's a powerful active region on the sun that then gives rise to strong magnetic reconnection on the surface of the sun, and then this in turn can lead. Let me go back and do this one more time here. This is a flare. This is taken with the SOHO spacecraft. We see that flare. Then there's snow that develops in this picture. There's a coronal mass ejection that's seen to flow out directly toward the Earth. And all the white streaks that you see in this picture are really due to high energy particles from the sun that have basically blinded the CCD camera on board the SOHO spacecraft. So more of an artist's concept of this, more of a schematic of what's happening, is that there is a region of the sun that loses stability. A large blast of material may escape in association with this kind of loss of stability. Perhaps 10 billion tons of material can be emitted. This can sometimes be moving out at perhaps 2,500 or 3,000 kilometers per second. And if that interacts with the Earth, it can really lead to powerful geomagnetic storms that in turn can cause intense auroral enhancements and powerful currents flowing in the Earth's vicinity. And these are the things that are regarded as the most extreme kind of space weather events. Of course, modern society has many eyes in the sky, has many tools in our arsenal that are in space. This is really an old diagram now, but it really shows the number of spacecraft at the geostationary orbit, 6.6 Earth radii from the Earth center. Spacecraft at this location are very convenient for communication and other purposes. They appear to stay fixed over a given geographic location on Earth. And there's estimated to be several $100 billion US dollars worth of assets in space at this time that are all susceptible to the effects of the space environment. Now, the space radiation can be very severe. Solar particle events can cause huge problems for humans in space and for sensitive electronics in space. The radiation belts around the Earth, Van Allen belts, the trapped radiation there, and geomagnetic storms in that vicinity can cause significant operational problems for the nearer Earth kind of systems. And a persistent problem is galactic cosmic rays that come into our vicinity from outside the solar system. And these can also be very detrimental to human and other biological forms, and can also be very damaging to spacecraft systems. So there's been a lot of discussion about the different aspects, single event upsets, the deep dielectric charging, surface charging. an article in Science a number of years ago really made the case that that all of these things can be very challenging, and they have just increased in significance for as we've become more and more dependent on space systems. Back in the around the year 2000, there was an activity cycle that was pretty powerful. This is an image of the sun in July of 2000. About 6.5 hours later, with the same camera system, we now see again that this was essentially blinded by the huge number of charged particles from the sun that were getting in and passing through the camera system on board SOHO. It doesn't take a lot of imagination to think, rather than a CCD camera, of a human eye or human brain in space and being bombarded this way with very energetic particles as a real risk for not only silicon life forms, but also carbon life forms. And of course, the high energy radiation around the Earth has been one of the topics of great interest to me. The energetic electrons that are in the Van Allen radiation belts can material, and if they build up fast enough, there can be the equivalent of an electrical discharge, almost like a lightning strike in sensitive electronics. And this can cause actual physical damage and has caused the disruption and even the physical loss of spacecraft in many instances. This is one case that we studied quite thoroughly back in the 1990s when the Canadian communication satellites, the Anik satellites, were knocked out of commission by deep dielectric charging episodes. So there are many drivers. Many drivers have been around for a long time about space weather challenges. There are many new emerging kind of evolving landscape, I guess you could say, new technologies and capabilities that will demand that we have even better space weather understanding and forecasting. The precision navigation systems, GNSS. In the US, we rely heavily on the global positioning satellites, but there are other systems around the world. The next generation air transportation system has a very strong space component. The power grids around the world are increasingly vulnerable to the effects of major geomagnetic storms, much more commercial satellite industry than we've ever seen before, and exploration of the moon and so forth. The GPS case is an interesting one in point. These are in 4 Earth radii from the center of the Earth, sort of circular orbits. And they were originally a military system for position and navigation. And over time, these were opened up for civilian use. And there's been a strongly emerging utilization of these for a wide variety of different purposes. And this table just shows the growth of the sort of dollar value of the business associated with this. And today, it's estimated that 1.5 trillion US dollars is involved with using GPS in all of its different manifestations. And this is the positioning, but surveying, construction, seismic data collection, you know, everything imaginable, as well, of course, the use for airlines and for naval and other operations. And one of the interesting uses of GPS, of course, has been to try to go from using ground stations. I apologize here that I'm often using North American kind of examples, but you get the idea. But being able to use instead global positioning satellites to tell aircraft where they are and how close together they are and so on has really been important. So the wide area augmentation system has been envisioned as a way to really eliminate the need for ground systems. But in the powerful storms of October 2003, the global positioning system, the WAAS system, was incapacitated for over 30 hours because of the great increase in the ionization, the great increase in the electron density in the ionosphere. Here, blue is good for communication, and red is bad. And as this storm developed, basically all of North America was made inaccessible by the increase, the dramatic increase in the total electron content in the ionosphere. So the ionospheric disturbances can cause a variety of problems for the global positioning and equivalent systems. Ionospheric ranging errors, scintillations. This can affect both the signals propagating through and causing range errors for users beneath the ionosphere. Can also cause just fluctuations and scintillations in signals. And so this much effort is being expended to reduce the effects of this through innovative engineering solutions, but this is still a major challenge. Another thing one might think is rather outmoded or in the past, but it's not, and that is really that airlines rely heavily on HF, high frequency and very high frequency radio communication, and a solar flare can basically cause radio blackout on the sunward side of the Earth. The entire day side of the Earth can be affected and require that one change to different frequencies, or may cause complete loss. And we're now entering into a new solar cycle, cycle 25, with increasing occurrence of new activity on the sun, and this remains a problem for airlines and others using high frequency communication. So another relatively, comparatively late development has been the fact that airlines that used to fly lower latitude kind of lengths are now using flights over the polar regions, here, for example, from North America to Asia. And this is, again, a somewhat old chart, but it really illustrates the point. The aircraft need to remain in contact with their company as they fly their routes. At higher latitudes, the communications are not possible, and they really can't use satellite communication. And so they really need to use high frequency radio communication. And if there's a powerful storm, as again I illustrate with the Halloween storms of 2003, this red area is where there was powerful precipitation, relativistic proton precipitation over this broad swath. And so this entire area over the high latitude region was blacked out. And for those kinds of events, the airlines have to fly, either cancel flights or fly at lower latitudes, longer distances, bucking headwinds, and it can be very costly to them to have that situation. And of course, we shouldn't lose sight of the fact that there's more activity and more planned human spaceflight activity now in our future. The International Space Station continues to be active, of course, and excuse me. And when there are energetic particle events from the sun or enhancements of the radiation belt particles, this can represent a significant risk to astronauts on the space station, and will be even more so as spacefarers go outside of the protective envelope of the Earth's magnetosphere. I was privileged to chair for the National Academies a committee that looked at the space radiation hazards for space exploration. This, again, was a number of years ago, but remains valid today. And in this study, we tried to gather the best information we could about what the risks were for space radiation for human spaceflight. And this table from that report back in 2004 lists the concerns: cancer-causing effects, degenerative tissue effects, damage to the central nervous system, acute risk. Death is a bad acute risk. But the range of effects is really quite staggering. And as one contemplates flights to Mars, for example, more than 6 months outside the protective envelope of Earth's magnetic field, the odds of having a space weather event, a powerful solar storm, are significant, and the damage, the devastation to the crew from a very energetic particle event could be quite severe. In about 2008, at Space Weather Meeting here in Boulder, I raised with government officials the fact that whereas there had been a lot of economic studies of economic impacts of other kinds of hazards, there really hadn't been those hazards being such things as earthquakes, floods, hurricanes, and so forth. There really hadn't been a very systematic examination of the economic and societal impacts of severe space weather. And so it was agreed that there should be a workshop where we began to make such an assessment. And so at that workshop, we had attendees from academia, industry, government, and we really wanted to look at what are the threats to these different endeavors, to these different areas of human activity, and what would be the benefits of improved space weather forecasts. And so this led to a report. My understanding is that this continues to be a popular report from the National Academy Press, and it's been translated into a number of different languages and so on. And so this severe space weather impacts remains something that that people have been trying to get their arms around, an understanding of what the effects are. But in this report, we showed this diagram, which I think came from our Department of Homeland Security, but it makes the point that we have a highly interdependent society, and this is true around the world. But electric power, for example, without bulk electric power, we rapidly lose so many other components of societal infrastructure that we depend on. Transportation is severely affected, emergency services are affected, government services are affected, pumping of gas and oil, the fuel supply, communication systems can be severely disrupted, losing ability to get potable water, banking and financing can be greatly disrupted. And so all these things are interdependent. And the knocking out of the bulk power would be a major and has been a major catastrophic event for regions or perhaps on the continental scale. These making an estimate of what this might mean during a powerful storm has been an undertaking. This is, for example, work I think from John Kappeman, looking at a powerful storm that occurred back in 1921. This was one of the largest storms on record. But translating that to more modern US kind of picture here. And what this portrays is the high voltage backbone for the US power grid system. And the reds and greens here indicate what the storm, the 1921-like storm, would lead to as far as current flowing into and out of these backbone power grid lines. And the outlined region here shows what would be a region where there might be a huge number of transformer failures, and that might lose power over this entire sector. In 2011 or so, I think there was an event that was just in a region here where power was lost for several weeks, and the economic effects are tremendous. So the electric power grid, probably around the world, but certainly from what we've seen for North America, is increasingly vulnerable to the effects of powerful geomagnetic storms, ground-induced currents, as they're called. This can lead to a burnout of large transformers and cascading effects that have certainly occurred in the past and are likely to occur again. And so the loss of electric power on a continental kind of scale would be truly devastating to modern society. The event that's usually thought of as the prototype for an extreme event is the Carrington event of 1859. This was the first white light flare that was really seen by scientists. Richard Carrington observed this, as did others, back in 1859. There were powerful solar protons associated with that, but also aurora were seen. You might enjoy this if you were in India, seeing auroras down to your latitude. But the facts were that aurora were seen in the Western Hemisphere down to Cuba and so on, and that there were immensely powerful aurora. People could read newspaper in New England by auroral light. It caused significant effects for the internet of that age, which was the telegraph system. Sparking from the wires, just the induced currents in the telegraph wires, caused fires and actually loss of life associated with the effects from this. And so it was a very, very significant a double whammy here of powerful storms that were associated with a very strong solar storm. So these coronal mass ejections can produce geomagnetic disturbances. You know that this is an important issue when the Washington Post picks up on it and has its own graphic, but really illustrates the idea that a coronal mass ejection coming out under the right circumstances with the right kind of conditions, this could interact with the Earth's magnetosphere, causing these kind of huge geomagnetically disturbed conditions that could induce powerful currents at mid and low latitudes and have quite significant impact. There have been a variety of different, let's say, insurance companies and economists who have tried to assess what the potential economic impacts would be for such, for the most extreme events. And there's some variation of this, but some estimates run to the trillions of dollars. That if you were, for example, to knock out the large, extremely high voltage transformers and a number of those, and it would take not months, but probably years to replace those. They're specially built. The recovery time could be extremely long, and the consequences for society could be quite staggering. I might say, well, the Carrington event was a long time ago, and that really wouldn't happen today, would it? Well, we just went through a pretty weak solar cycle, the solar cycle 24. But even then, back in 2012, there was a powerful an active region on the sun, or several active regions that converged. And as they went across the disk of the sun back in July of 2012, they were popping off coronal mass ejections that had pretty interesting effects. But about 10 days after what I just showed you, 8 or 10 days, the Stereo spacecraft, which was on the far side of the sun, was observing the sun. You see the sun in the center there in UV, and then you see the coronagraph, and you see a huge halo kind of coronal mass ejection that approaches the Stereo spacecraft directly. And that was a pretty ugly, pretty active region. And this has been modeled. Here we're looking down on top of the sun. We're looking at the Earth here, a number of assets. So this is kind of NASA interested modeling, but the Stereo spacecraft was over here. So the events we're talking about for a bit later in July really occurred after this active region had gone beyond the west limb of the sun and was popping off coronal mass ejections that actually interacted with the Stereo spacecraft. We posed the question, what if the Earth had been here at the Stereo spacecraft location, or what if this most powerful of the coronal mass ejections had occurred a week or 10 days earlier when the Earth was in the line of fire? And so in a paper published in Space Weather Journal, we looked at that. We had measurements from stereo of what the magnetic fields were. We had measurements of what the solar wind speed was. We have the measurements of the density. The largest storm of the 20th century that was actually measured at Earth was in 1989. This was about 589 nanotesla for the DST index. Our estimate, and this is only an estimate, of course, but that the DST, equivalent DST that would have occurred for this particular set of conditions that were seen by stereo A would have been that this would have been at least twice as large, like a 1200 nanotesla DST storm, which would have been amazing to behold. And I've said in public and private that if this had occurred, we might still be picking up the pieces if the Earth had been in the line of fire for that. This has been examined by other workers. Ying Liu, for example, also examined this in some more detail. Our friend Dushan Adrasil has modeled this even more actively. This is a slowly developing animation, so I can talk about it a little bit more, but this is the same kind of picture you saw before, where now the solar wind velocities are measured and have been modeled as well by the Enlil model. But what I would point out here is that there was a coronal mass ejection that occurred a couple days before that sort of cleared out the inner part of the solar system. And then this most powerful one came out and had pretty free access, was able to move out very unimpeded out toward the stereo A location. And this may be a feature that during active times, you may have a clearing out of the impediments, and so that the largest of these coronal mass ejections may have ready access to the Earth, or the equivalent location of the Earth. Now, it's important to remember also that we've seen some weak solar activity cycles as measured by sunspot number, but that the 1859 storm, the 1921 storm that I mentioned, the storm I was just talking about for July 2012, these have all occurred during times of relatively weak solar sunspot maxima. And yet the sun is perfectly capable, even during weak solar cycles, of producing very powerful geomagnetic and solar storms. I'm probably a little long on my time here. Let me just make a couple of remarks that we've found that having good monitoring systems is a crucial part of the picture. We had from 2012 to 2019 the Van Allen probes, the radiation belt storm probes that were making measurements of the radiation belts around the Earth. These proved crucial for getting a deeper understanding of just how variable and how powerful the changes in the radiation belts can be. Here, for example, these are measurements from our relativistic electron proton telescope. Here we're looking down on the Earth. The spacecraft are in these elliptical orbits. We can make measurements of the particle intensities along the orbital track. The particles drift around the Earth much more rapidly than the spacecraft move, and so we can really use this to map around in sort of a dipole coordinate system, so we can get a space weather picture of the radiation environment. And we can see these are orders of magnitude increases in the radiation intensity that occur on very short time scales. And so the radiation belts can fade to almost complete absence, except for the relativistic electron storage ring, which I can talk about sometime. But the radiation belts then can pump up on the order of hours or even tens of minutes to much, much higher values. And spacecraft throughout the entire magnetosphere are subject to this kind of change. So this is a very direct way of saying that we can have almost our own space weather maps of the magnetosphere using these kinds of monitoring tools, but these are no longer operative since this Van Allen probes went out of business in 2019. Let's see if I can get my cursor back here. Pardon me for going backwards a little bit. So we have quite an armada of spacecraft. The Heliophysics Observatory fleet has given us tremendous insights into this. We are using both operational spacecraft, such as the geostationary orbit satellites of NOAA and others, and we are also using scientific satellites. But with this, we've been able to put together a good picture of what's going on, or what has been going on. When combined with the solar observations that I mentioned before, we've had quite a heyday of studying the Sun-Earth connection. But we make the point in the decadal survey. I was pleased to be able to chair the National Academy Decadal Survey that was published back in 2012. And in this, we really talked about how crucial it was to not rely just on sort of ephemeral scientific measurements, but we need a truly dedicated operational 24/7 in perpetuity kind of set of observations of the connected Sun-Earth system to have an effective forecast capability. So let me wrap up here by just saying that space weather, much of it driven by the sun, is a persistent and real issue. It is joined to other hazards, and when there are severe solar storms, these can affect the Earth in a variety of ways. The coronal mass ejections can cause significant impacts, can certainly cause effects on the power grid, can couple into the Earth's magnetosphere, ionosphere, can cause significant enhancements of the currents that are flowing in the upper atmosphere and ionosphere. These can couple into power lines and pipelines, can cause significant damage and can cause power outages. The effects of space weather extend as well to the ionosphere that can knock out communication, either high frequency reflection from the ionosphere or transmission through the ionosphere. Effects on the global positioning systems can have wide-ranging economic impacts, causing effects for GPS. In turn, this can affect precision agriculture, navigation at sea, and a whole host of other consequences that I've talked about. And of course, the effects on individual spacecraft as well as constellations of spacecraft are not to be neglected, and the effects can include sensitive electronics and also degradation of solar panels and things like that. And so when we have thousands or tens of thousands of spacecraft that can be affected, this is a very severe matter indeed. So solving the space weather problem or the puzzle requires that we have, of course, core space and ground-based observations. Also requires that we extend and utilize our core modeling capability and that we have improved forecasting. Together, these can really help us complete the picture to solve this puzzle that is with us. And I'll just conclude by saying that I think the challenges of space weather affect essentially all countries, high and low latitude in their way, both civilian and military systems. I contend that work on space weather, whether specification or modeling or forecasting, has great societal benefit. I characterize that as basic research with a high public purpose. And certainly future space exploration, both robotic and human, and most modern human endeavors really require that we improve greatly our physical understanding and improve the transition of space research, basic research, to operations. And finally, I would just say, U.S. professionals need to think about this very much. How do we deal adequately with what I think is a real, very space weather threat without being unduly sensationalist about it? So how do we avoid the Chicken Little syndrome that the sky is falling? I'm pleased to say that there's been a lot of political action, a lot of political activity, especially in the United States, and that policymakers now understand that space weather has joined the pantheon of natural hazards, earthquakes, fires, floods, and has come to understand that this is a hazard that's with us and needs to be dealt with. So with that, thank you, and I'd be happy to address any questions.
Thank you, Professor Baker, for this fascinating talk touching upon and clearly elucidating various aspects of space weather and its societal and economic impacts, and also, in terms of pure science, understanding that we need to gain as well, that you just touched upon. I'm sure there are a lot of questions. I'll request my colleague, Professor Chakravarti, to conduct the question answer session, please.
Thank you, Raju. I'd be happy to answer any questions I can.
Sure. Yes. Thanks.
I see one question in the chat box
Okay.
that
Would you like to read it to me, or
yeah,
I
I'll
can...
read
Okay.
it for you. The question is from Bhaskar Mukherjee. The question is, how effective is a simple ground level neutron monitor to predict space weather fluctuations?
It may not be so effective for prediction, but it's certainly for assessing the strength of it and understanding how strong how high in energy the radiation from a particular flare or coronal mass ejection is. It's pretty crucial, and of course this represents one of the longest records that we have of these kinds of extreme events, and so continuing to have these kinds of measurements is really crucial going forward. And this is one of the things I guess I would point out is that research may be somewhat flighty. It may flip from one kind of topic area to another, but we really need to have long-term continuous records of these kinds of events and these kinds of disturbances in order to understand them more deeply. And if we didn't have longer-term monitoring, I think we would be in a very challenged state to understand the long-term space weather behavior.
Yeah, thank you, Dan. There is a question from Professor Anil Bharadwaj.
Okay, I'd be happy to.
Thank you, Dan. Thank you for a very excellent talk and for a nice coverage of both the research aspect as well as societal implications and impact on economy. And we know that all countries get affected because of space weather in many different ways. India in particular, being in the low latitude, is not too much affected by certain aspects of space weather, but we do get affected. So my question to you is that in US, in particularly the government, how is that support for space weather research, both in terms of modeling and predictions, as well as in terms of understanding its implications on the society?
Yeah, it's a very good question. And first, with respect to your point, yes, and I apologize that I gave sort of the perspective of a mid-latitude person from North America in my remarks, and I certainly recognize that space weather has different faces at different parts of the world and different latitudes and different times. But I would point out that during the most extreme events, you may be seeing at low latitudes things that are more regularly experienced in Scandinavia or northern Canada or something like that. And so don't be surprised during the most extreme events if you are seeing GICs in your power grids as well. But let me say that with respect to the core of your question, I've been maybe in some ways pleased and impressed that over the last decade or so, through the efforts of a lot of people, policymakers, the government agencies have taken space weather much more seriously. There have been congressional bills that have recognized the importance of space weather. Budgets have been increasing in key areas. Agencies like NASA that I used to think that was only for the applied agencies, not for the research agencies, are now stepping up more to their responsibilities. And so I would say that space weather has gone from being something that the average person on the street or the average politician didn't even know existed, to being much more recognized as a significant matter for society and something that needs to be dealt with. So I hope that that will continue. I hope that we all, worldwide, will continue to help our populations and our politicians understand that this is an important issue, a set of issues, and that we have to be prepared to deal with this as a threat, as we are prepared to deal with other kinds of natural hazards. Excuse me. I hope that answers your question.
Thank you, Dan.
Can I ask a complimentary question to this?
Yeah,
Sure.
please.
Okay, thank you. So the related question is that we do see now a change in solar activity with respect to the intensity of activity.
Mhm.
So how do we perceive space weather impacting the society and economics in coming decades with the decline in the solar cycle activity?
Yeah, right now we are on the upswing for the new solar cycle. It's looking like there's quite a bit of activity. It may not be the largest, largest solar cycle we've ever seen by any means, but the forecasts are that we're going to be moving toward a sunspot maximum in about 2024, 2025 or so. And as I indicated, when that happens, even if we don't have a bell ringer of a solar cycle, we could still have very powerful solar storms. And so the other thing that you well appreciate is that our vulnerability to space weather has continued to go up because we have more and more systems that are dependent on space, a leg in space, or that are dependent on satellites, or that are more sensitive to the effects of currents, induced currents, and energetic particles, and so forth. So we're building in more and more vulnerability into our technological systems and they're becoming more complex and interconnected, as I tried to illustrate. And so I think it's not a question of if we're going to have significant effects from space weather, but when. And the probability that we're going to have significant cascading kind of effects from intense space weather are just increasing year by year, solar cycle by solar cycle. I really believe that's true.
Yeah, thank you. Thank you.
You're welcome.
Yeah. Thank you, Dan. The next question is from Professor Dipankar Banerjee. Dipankar, please.
Yep.
You are muted, I think. Dipankar, you are muted. Dipankar, I see you are muted, so.
Myself.
Yes.
Sorry, I was not able to unmute myself. I think it was a system error.
Okay.
Sorry, Daniel. Thanks for the nice overview. I think it's a continuation of what Anil was mentioning about, our less effectiveness of space weather in our latitude. But I must point out that we are going to have many more space assets. And with our own space manned mission, this has been actually a very, very important topic. And in fact, we are hosting a meeting in 2 weeks' time for space radiation workshop with NASA colleagues. So my question is, yes, from India also, we are taking this as a very serious, subject area, space weather and space radiation, particularly for our space, programs. Now, what is the current status of your new mission, avenues from US, particularly say for L5. Is there any update on that?
Well, yes, I think there's a recognition that that this is a crucial step to be able to get a more complete picture of the sun and to be able to see not only from the L1, directly toward the along the Sun-Earth line, but to be able to see what's coming around and what might be affecting us in the next week or 2 weeks or something like that. In fact, I'm part of an organizing committee for National Academy and also on some advisory groups for NASA that I think are taking very seriously the need to that we have to have a more 4-pi, complete look at the sun and know what's going on at other longitudes behind the sun. What active regions are coming around, and we also need measurements at high latitudes. We need pole sitters so we can really see what the magnetic fields are, what complex magnetic fields are at the higher latitude on the sun in order to do a good job of modeling. To your specific point, I think both NASA, NOAA, and some Western European countries like the UK have really recognized that extremely desirable to have measurements at L4 and L5 and to be able to get this more complete picture of what's coming, both as far as solar energetic particles, but especially what's coming as far as solar active regions, and being able to forecast with, or at least have more effective alerts of whether active regions that might potentially be causing these largest coronal mass ejections might be coming. I think this is a team sport. I think that we should all, the world should be pooling its resources and assets in order to get this more complete picture of the sun. I hope that will happen. And let me say again that if I had maybe more time or more had tailored my remarks more, I could have emphasized the lower latitude impacts of space weather, the ionospheric impacts, which I know affect all of you greatly. And I've tried in these remarks to just give a broad brush kind of look at those things. But when we move into space, or when you start putting more satellites into space and you start putting humans into space, we're all going to be affected for sure. So
thank you.
Yeah.
You're welcome.
Yeah. Dan, there are a couple of questions. I think you have already addressed those. One from Ramesh Singh and Dr. Ramesh Singh, and another from Dr. Tarun Pant regarding the effects of space weather over low and equatorial latitude. I think you have already addressed that. Commented on that. The next question I'll take up from Dr. Nirvikar Dashora, who is asking that how important is the electric grid data to delineate the effects of space weather events over low latitudes?
How important is making measurements of the grid's behavior and performance?
Yeah, based on that, whether you can infer the space weather effects over low latitudes. How important it is.
First of all, I think that having good measurements of the drivers, the interplanetary conditions and the magnetospheric conditions, so that you can model what those effects are at any particular point, any latitude, any longitude, would be extremely important. If a component of this question is how valuable is it to have measurements on the grid itself, I think the answer is very important. I think that this has been found, especially by our Canadian colleagues, that having direct measures of the effects locally and then relating that to the sort of geomagnetic conditions has proven extremely important. And something that has emerged relatively recently is understanding just how important the geology of a given region is. The ground-induced currents depend not only on what the drivers are from above, but what is the conductivity of the soils or the granitic underlayment or and so forth. And whether you're at a boundary between soil and seawater or so. All of these things have very significant effect on the nature and strength of the ground-induced currents and what couples into the long conductors and so forth. So this is an extremely complicated, it is a quite a complicated set of issues, and really requires a lot more work. And I'm delighted to say that a lot of that work is going on here in the U.S. Geological Survey and our colleagues here in the Boulder area, for example. So I hope that helps answer that question.
Yeah. Then there is a very important, very interesting question for you. Raghis Mishra, he is asking that for improved space weather forecasting, we need to better rely on observations or modeling. I mean, he is also commenting that the limitations are known as far as observations and modeling. Both the approaches have limitations, but he wants to hear from you that which one is more.
I'm getting a lot of static from somewhere, I don't know, but maybe it's a space weather event here that I'm hearing. But I would say that, it's hard to say that one is more important than the other. Of course, at the present time, we need to know what's going on in the system. So we need observations in order to be aware. But to know whether it's going to be an important effect for society or whether it's going to be ignorable is really largely a modeling statement. And so to have effective models, both empirical and physics-based models, and to be able to feed those models with reliable, robust observations. These go hand in glove. My little puzzle picture that I showed at the end really tried to make the point that you can have observations, but you have to have the models to really complete the picture. So I don't want to be a weasel about this. I don't want to evade the question, but I think that we have to have both effective observations of the global system, and we have to have effective models to ingest those data and use them to good societal effect. And that's really the truth.
The next question is from Dr. Deepti Ranjan Raut. He is asking that, is there any plan for future radiation belt missions from your side?
Yes, there are plans, and in fact, there are several missions that are in the works now. These are not the comprehensive kind of measurements that the Van Allen probes missions were. These are more based on smaller, more limited kinds of observational platforms. But I think using those and then using the understanding that we got with the very comprehensive measurements from the Van Allen probes and the Arasi mission from Japan, I think that we're going to be able to sort of make it through. I personally have been advocating that we again revisit the question and try to have something more approximating the comprehensive nature of the Van Allen probe mission as an ongoing, in perpetuity kind of operational system. We call this ORB, the Operational Radiation Belt mission, and having multiple petals of the sort that the Van Allen probes had, and being able to make measurements across the entire spectrum of particles, I think would be extremely valuable. And it wouldn't, in the whole scheme of things, would not be that costly, and it would be very effective for the long-term health of the space weather enterprise. And that is gaining some traction, I believe, with policymakers and with the agencies. And I expect that the budgets are going to reflect that over the next few years.
Yeah. There is a question from Dr. Sardar Singh Rao. Although he's asking this question for Indian sector, but I think you can sort of give an answer in a more generalized manner. He's asking that the chain of magnetometers, for example, over Indian sector, around 75-degree longitude, there is a chain of magnetometer stations that are available for space weather studies. And so how important it is to monitor space weather, let us say over Indian sector and over other sectors. So he is asking.
Yeah, extremely important. Yeah, it's a great point. And having ground-based measurements and having effective, well-calibrated, well-understood measurements in different meridians is has proven extremely important, and would again be a key component of what I was talking about before, to have ground truth about what's really happening, and being able to use that in real time or near real time in order to inform the system of what's going on, and where GICs are being concentrated and things like that. This is really crucial stuff. And so I think that the more we have effective ground-based tools that can be combined with space-based observations, the better we're going to be able to do in the enterprise I was talking about, of having a really effective operational space weather system for the globe.
Yeah.
Very important.
That Shivam is writing, I'll just read it out, what he has written for you.
Okay.
Sir, I have a question. As the temperature of sun is very high, how can it be possible to do missions on sun?
Can you repeat the question, please?
Yeah, he is asking that the temperature on the sun is very, very high. So how is it possible to do a mission on sun? That is what he is writing.
Yeah, we used to joke that the way to do the solar probe mission was to do the mission at night. But this really has been the challenge for the Parker Solar Probe, is to be able to go close to the sun and deal with the intense heat of the sun. And by having carefully designed shields, ablative shields, that has worked quite well. As you know, the Parker Solar Probe is approaching closer and closer all the time to the sun, to the region where the solar wind is actually accelerated at a few solar radii. And so it is an engineering marvel, I guess you could say, that one can build spacecraft that can withstand those intense solar heating and still function effectively. The way these shields work is that the instruments are all behind the ablative shield. They're operating, in a pretty comfortable environment, and are still able to make the relevant measurements. And I'd like to say that these instruments are at room temperature, but as one American comedian noted, whatever room you're in is pretty much room temperature. So it can be sometimes an uncomfortable room. Sometimes it can be a pretty comfortable room. But anyway, I believe that the design engineers have really mastered this pretty well, and have found ways to be able to deal with the intense heat of the sun and still be able to make effective measurements.
Thanks, Ren. The next question is from Rajesh Kannan. He is asking that does space weather affect biological processes?
Yes, the biological, I guess there are many facets to that question too. I think in the old Soviet Union, there were a lot of studies that suggested sort of complicated either psychological or physical effects of storms on human behavior and things like that. I can't comment too much about that, but we certainly know that there are significant biological effects from space weather events. A notable example, sometimes it's looked upon as maybe amusing, but homing pigeons, for example, can be disoriented by powerful geomagnetic storms. In fact, the pigeon racers in North America are some of the most avid users of space weather forecasts, because if there's a major geomagnetic storm, their pigeons can get lost, and they have suffer significant consequences from that. But by extension, there are many biological systems that are sensitive to magnetic fields. Changing magnetic fields can disorient things. And of course, humans can probably have some sensitivity to that as well. We certainly know that many industrial processes can be severely affected by space weather, and knowing when there's a major geomagnetic storm in progress, or shielding against changing magnetic fields, has been very important for plasma, fabrication processes and stuff like that. So the amazing thing about space weather to me is just how far wide-ranging the effects really can be, how dramatically different sectors can be affected, and how differently they can be affected one from another.
Yeah. In fact, as a continuation of what you just said, and Ankit is asking that how severely a severe space weather event can affect the economic activities.
Yeah.
So I think you have already
discussed. Yeah, I think if you consider not only the direct effects, of spacecraft lost or something like that, but you also consider just the day-to-day, more routine weather and how it affects the efficiency of operation of our technological systems. The integrated effect is really quite significant, and I still believe that we haven't, as a space weather kind of community and as economists, haven't really fully assessed what the economic impact of all kinds of space weather really is. I think that's work that yet needs to be done.
Dr. Shashikiran Ganesh is asking that, would you please comment on what studies of the geological and meteoritic records tell us about long-term history of space weather in the solar system?
Yeah, that's a very interesting, very good question. Looking at tree rings and ice cores and so on has taken things back quite some time. One of the most intriguing things, I suppose, that's emerged in relatively recent times was looking back at the year 774 or thereabouts. There was an immensely large signal in tree ring in the amount of carbon-14 relative to carbon-12, and I think more examination of that has really suggested that that was probably a solar storm that was much larger than the Carrington event, or much larger than any other event that we've seen in the modern era. So these kinds of records, the complex atmospheric effects of solar energetic particles that then get swept up into the atmosphere, might embed themselves in tree rings, or could register in the signatures in ice cores, really represent one of the best ways we have of looking back through time to see how extreme space weather events might really be, what kind of variability they have exhibited over thousands or tens of thousands of years. It would be highly desirable if we could really disentangle this more and really get a clear record going back millions of years to when the sun was more active than it now is. But I think researchers in these domains, in the atmospheric and cryospheric areas, are really trying to push this as much as they can. I didn't realize how controversial a lot of these things are, how challenging they are, how many things can affect the ice cores, for example. And sometimes I think space physics is controversial, but some of these other areas of science get even more wild and hostile. And so the records don't necessarily always comport, but when you see something happening at many locations around the world at the same time, you really get a sense that this must be a global, not a local effect. And I think this 774 AD event is now generally agreed to have been a very, very substantial solar event and might be indicative of just how bad it could get.
Yes, okay. Thank you. And next question is from Professor Pallam Raju.
Mhm.
Yes, Dan. Yeah. What kind of, when you're talking about the drilling and in the oil and then the survey work, you're saying that there are errors in those aspects when they're drilling. What kind of errors are we talking about? Can't we solve it by corrections with multiple satellites giving the data?
Again, Roger, I would say that yes, people are trying to use dual frequency and other things, multiple frequencies, to try to eliminate any uncertainties about positioning. I'm not an expert. I'm not an expert driller, but what I've understood is that, for example, the drilling, deep sea drilling, that they have to know things to exquisite precision. If there's any significant uncertainty, that this can really completely disrupt the effectiveness of the drilling system, and so that they would rather just know, is it all clear? Are we going to have quiet conditions, or can we and we can therefore carry out our business, or if we're going to have disturbed conditions, we'll just shut down and not carry out drilling operations during that time. But implicit in your question is something I suppose that we all think about, which is if there's a known space weather effect, can't we engineer around it? Can't we figure out a way to avert that effect and thereby solve our problem? And one of the issues is that we're developing new technologies all the time, new approaches all the time, and we don't know how susceptible they are to space weather until they're often up and operating, and then only then do you realize that you've got some new vulnerability, and so then you have to figure out a way around that. We're putting new electronics in space that has susceptibility. We're putting new materials in space that are highly susceptible to effects of space weather. I think often our creative technology is outpacing our understanding of what the likely effects of the space environment are, and I think we need a more systematic approach to assessing and averting the effects of space weather. That's what society really needs, and I don't think we right now have the will or the capability to do that in as effective a way as we should.
Okay, thank you.
And I haven't even mentioned in this talk what I've largely failed to mention what I would call anthropogenic space weather. There are many things that humans are causing, and one of the ones that worries me most is launching wholesale, constellations of spacecraft that are going to be creating debris, which we're going to be creating our own space weather here, and we already have, and this is something that really needs policy attention. I hope you can use your meeting for the next couple of days to solve all these problems, by the way, Roger. Okay.
That would be wonderful. Great. Thank you.
Yeah.
Yes.
Yes.
Let me know when you get all the answers, because I'd like to hear. Okay.
Dan Sohan is asking that how much in advance we can predict space weather.
Yeah, that's a very good question, and it's a crucial question for the users or the operators who have to deal with space weather. We often, in some of the policy things I've been involved in, we've tried to ask questions. For example, if you're a power grid operator, what would you like to know and when would you like to know it? And we're told that they would like to know like one shift, 8 hours or 12 hours in advance that there was a major storm. They'd like to know how large the storm is going to be, when is it going to hit, where is it going to hit. They're asking for kind of precision of knowledge that I don't think we can offer right now. But this again varies depending on whether you're a spacecraft operator, whether you're a power grid operator, whether you're a farmer out, using GPS. Each of these have somewhat different answers to that question. But in my opinion, the single most important space weather knowledge that we could have would be when we see a coronal mass ejection leaving the sun, if we could know pretty precisely what the strength and orientation of the magnetic field was within that coronal mass ejection, and could therefore model how strong the resulting geomagnetic storm and GICs were and stuff, that this would go a long way to solving the most extreme space weather prediction issues that we have. But I can't say for every kind of susceptibility, but I would just say that we do, by working with operators and stuff, we have a pretty good understanding of what each of those different businesses really need as far as knowledge of how much warning, how much forecast, how accurate they have to be, and so forth. I think we're getting a better handle on that all the time.
Yeah, thanks, Ren. And the last couple of questions I'll take. But before that, I just want to say that there are many questions that have poured in, even on our YouTube channel. But it's not possible to probably accommodate all the questions to you, Dan.
Okay.
So just post the last two questions because of the paucity of time.
Mm-hmm.
And the next question is from Dr. A.K. Upadhyay. He's asking that, is there any plan for any future space weather mission to any non-magnetized planet?
Well, I don't know whether you consider Mars a non-magnetized planet. It has localized magnetic field, but there's space weather at Mars. There's space weather at Venus. We know that these planets that have don't have particularly significant global magnetic fields, don't have the kind of active magnetospheres of the Earth or Jupiter or even Mercury. We do know that there's still space weather there. Excuse me. And we expect that there are going to be missions there. We're now engaged in planning for a new mission that will go to Venus, and then we'll go on to small bodies, asteroids. And there too, we're going to need to know what the environment is in order to be able to function, to be able to do effective navigation and flybys and things like that. We really we need to make sure that our systems are not going to be adversely affected by the environment. So anything you do in space, whether you're in a region of a magnetized body or whether you're in free space, space weather can get you in a wide variety of ways. So we need pretty comprehensive knowledge, frankly.
Yeah. I see a raised hand, Nandita, Professor Nandita Srivastava.
Yeah. Thank you, Dipu. Dan, I had a question. It's relatively easier to predict the impact of a source CME rather than, if you think of a stealthy event, which may also give rise to a strong storm sometimes, but prediction becomes complex. So what is the way forward? What is your view about it? Because that may act as a missed alarm kind of a thing.
It's a very good question, and of course, probably the most scary, severe thing you can think about there is that there's an active region on the sun that we can't really see, but that the magnetic connectivity is such that very energetic particles might arrive very promptly from something that we really don't know is going to hit us. There again, I would say that maybe our best shot at this is to have a more complete picture of what the sun is doing, to have L4 and L5 kind of observations as well. So we're we're getting a broader picture of what might be happening. And the other thing is, I guess I would have to say that we're never going to be 100% accurate, 100% aware, and goes back to probably what Raju was saying to me before, is that can't we understand deeply enough what the effects of the space environment are so that we can make ourselves more immune to the effects in the first place? Engineer better systems. We can't engineer away all the problems, but we can make ourselves more secure than we currently are. And I have real fear that a lot of systems are being just, I don't want to disparage anyone who loves Radio Shack or loved Radio Shack, but having just a very haphazardly designed commercial systems may mean that we're going to have a lot more susceptibility than if we took more care in the design and construction of both ground and space-based facilities.
Yeah, thank you.
So I probably have exceeded my time, Deepu. I want to thank everybody for the excellent questions and your attention. I hope I haven't droned on too long about this, and I want to wish you all the best for the workshop that you're going to have for the next couple of days. I hope it'll be a great success. And again, I look forward to my next visit to India.
Thank you so much, Dan. And it's pleasure having you today on this occasion.
Well, thank you. It's been a pleasure for me to be part of this, and good luck with everything. And I'll leave it to you to answer all the questions that I didn't get around to on YouTube. Okay.
So,
okay.
Yes.
And before I hand it over to Professor Pallam Raju, I apologize that we couldn't accommodate the lots and lots of questions and comments have poured in, and it's not possible to probably accommodate realistically in a single talk. I mean, there are huge number of questions and comments. So Dan, your talk has evoked a huge response from the audience. So thank you so much.
Well, thank you for the opportunity. I appreciate it very much.
Okay.
So, over to you, Raju.
Okay, thank you, Deepu, for conducting this, pretty long but very nicely and engrossing question and answer session. Thank you. Just before we end, I think I'll call upon Manas Samal, my colleague, to conclude the session. Manas, please.
Thank you, Professor Pallam Raju. Friends, it is an honor to propose vote of thanks to all who have helped us in making today's vacation possible. First of all, I, on behalf of PRL, would like to thank today's speaker, Professor Daniel Becker, for accepting our invitations and agreeing to share his knowledge with us. Professor Becker, we are truly thankful to you for explaining us various aspects of space weather phenomenon and their socio-economic impacts in a very simplistic manner, and also suggesting us how can we improve or prevent the negative impact on our society with future scientific advancements. In fact, there are question and answer session, and the question answer session was very engaging and informative exchange of ideas. That was great. Thanks for taking all those questions and answering them patiently. Once again, I thank you for your time to share your knowledge and wisdom with us.
Thank you. Thank you very much.
Yeah. Thanks to Professor Anil Bharadwaj, Director of PRL, Professor Pallam Raju, Dean PRL, and all the Vakyan committee members for their continuous efforts to make this Vakyan series keep going. Finally, on behalf of PRL, our special thanks to all our participants and panelists who have joined us through WebEx, WebEx platforms and YouTube platforms, and putting a lot of questions and making this Vakyan series more, more informative and exchange of ideas. Thank you all for your time. With this, we come to the very end of today's chapter of PRL's Amrut Vakyan. See you next week with another 8 interesting Vakyan. I just want to emphasize that next week's Vakyan will be again at 10 a.m. So please join us at 10 a.m. on 9th January. Till then, goodbye to you all. Have a great day or great evening. Thank you.
Bye. I'll sign off now. Thank you.